Ladies and gentlemen, I'm truly honored to welcome you all at the University of Warsaw for the presentation of the Włodzimierza Kołosa medal. This year the medal is awarded to Professor Anna Krylov from the University of Southern California, Los Angeles, in recognition of her outstanding achievements. This medal is awarded every 2 years, and it honors exceptional contributions to the field of theoretical and physical chemistry, and it is presented jointly by the Faculty of Chemistry at the University of Warsaw and Polish Chemical Society. Today we are joined by 3 special guests. Professor Artur Michalak, Vice President of Polish Chemical Society. Professor Robert Kołos, son of Professor Włodzimierz Kołosa and respected chemist at the Institute of Physical Chemistry of Polish Academy of Sciences. And Professor Joachim Sauer from Humboldt University, 2009 laureate of Kołosa Medal. It is an honor to have you here. I would like also to warmly thank the Kołosa Medal Committee for the hard work in selecting this year's laureate. The committee's dedication ensures that Professor Kołosa's memory continues to inspire and that outstanding scientists are recognized for their achievements. Today's program will begin with Professor Michał Lesiuk, who will tell us about the life and legacy of Professor Włodzimierz Kołosa. Just a moment. After that, Professor Michał Tomza will introduce the scientific accomplishments of our laureate, Professor Krylov. And following these introductions, we will move to the awarding of the Kołosa Medal, and then we will have the pleasure of hearing Professor Krylov's lecture titled Molecular Orbitals, Physical Reality or Mathematical Construct. So thank you all for joining us to honor Professor Włodzimierz Kołosa and celebrate Professor Krylov's impressive work, and let this event inspire us and in all our pursuits for knowledge and excellence in chemistry. So thank you for joining us today.
Hello everyone, I will just prepare my slides in a second and start my talk. So hello once again. I hope you can hear me well. In this short talk, I will give you an overview of Professor Kołosa, his scientific achievements and his legacy, and a bit about the Kołosa Award itself, the past recipients of this award, and a bit of history behind it. So starting with Professor Kołosa, he was born in 1928 in Pinsk, and his family moved quite early. When he was a child, they moved to Western Poland, near Poznań, and he received the Master of Science in Chemistry at the University of Poznań, which is now Adam Mickiewicz University, in 1950. Then he stayed in Poland for a bit longer. He undertook graduate studies in theoretical physics under supervision of Leopold Infeld at the University of Warsaw, and then started his PhD studies when he worked on topics related to organic chemistry of small molecules. And then after graduating, he worked in Poland, in Warsaw for a bit. He worked on extension of Thomas Fermi model to electron correlation on organic molecules. And then he moved to the States, to the lab of Professor Millikan, a huge name in quantum theoretical chemistry. And he joined his lab at the University of Chicago in USA. And it was there when he pioneered the use of early computers for quantum chemical calculations to solve quantum chemical problems. I will return to that and what he did precisely in just a bit. After returning to Poland, he worked for several years in Świerk, in Nuclear Science Institute in Świerk, and then he established Quantum Chemistry Lab, which I have a privilege to work in today, at the Faculty of Chemistry, University of Warsaw, and he worked there until he passed away. Notably, in 1967, he became the first recipient of the annual medal of the International Academy of Quantum Molecular Sciences, a very prestigious award back then and now. And he became full member of this society in 1988. Of course, he was also a member of Polish Academy of Sciences since 1969. And he unfortunately passed away in 1996 after a period of illness. So after this brief recap of his career, let me discuss what were topics of his scientific work, what was his main contribution to quantum chemistry and molecular physics. So he is very well known, maybe most well known for his precise calculations for molecular hydrogen, and many of you will know the story that when they did calculations for hydrogen using first computers, there were also measurements of this quantity from Herzberg, who later received Nobel Prize, and his calculations were based on variation principle. So all of you know that technically the result obtained from variational principle for the dissociation energy should never be larger than the experimental one, because the variational principle gives you an upper bound. However, when he did the calculations, it turned out that not only there is some discrepancy with respect to experiment, but also the result is larger for the dissociation energy. And this was a puzzle. They redid calculations at high precision. They accounted for relativistic effects or other corrections, but nothing could explain it. And in the end, it turned out that there are only two possible answers. Either there is something wrong with experiment, or there is something wrong with quantum chemistry or molecular quantum mechanics, to be more precise. And fortunately, in the end, it turned out that the experiment has to be redone, and they solved this discrepancy after the next measurement. But this gave us confidence that quantum chemistry, quantum mechanics provides an excellent description of molecules, and bolstered our faith that this is the correct theory of molecules in general. So by these calculations, he also pioneered both computational chemistry, so computational chemistry when you use computing machines to perform basic operations, but he also was a pioneer of something that we would call today ab initio quantum chemistry. Back then, many calculations were done with empirical models or semi-empirical models, but he was one of the first who did calculations using pure theory without any empirical data, which could be directly related, directly compared to the experiment before the experiment was even made, so without any reference to prior experimental data. So he is also very well known in the same line for determining various spectroscopic properties of grounded excited states of hydrogen molecule. Together with Professor Włodzimierz, they did calculations for hydrogen, including quite sophisticated relativistic, non-adiabatic corrections, which were necessary to pinpoint this really accurate result. And over decades, this continued, and this comparison between theory and experiment continued for hydrogen. And there were new experiments done, there were new calculations done, And a few years back, a new set of calculations was done for hydrogen, and theory, again, now is more accurate than experiment at the moment. This changed back and forth throughout the history, but you can see that the legacy of Professor Kołosa lasts until today. And until today, we do such calculations, and we still believe that it's really worthwhile to make such accurate predictions. Besides hydrogen and accurate calculations for hydrogen, he did a lot of different things, including, for example, theoretical studies of molecular effects in beta decay. And the main motivation here was determination of neutrinos' rest masses. His results were used to determine, in some compound method, to determine rest masses of neutrinos. So you can see that his results were useful not only in chemistry, but also very interesting for physicists. Another big topic that he worked on was muon-catalyzed fusion, and he performed very accurate calculations for diatomic systems. And he took into account both the Coulombic and also strong nuclear forces between the nuclei to model interactions between tritium and deuterium nuclei. Of course, he also made numerous contributions to quantum chemical methods, in particular to perturbation theory of intermolecular forces, which eventually culminated in what we call today symmetry-adapted perturbation theory. He is definitely one of the fathers of this theory. Throughout his career, he received numerous awards, including, for example, Alexander von Humboldt Award or Medal of Israeli Academy of Sciences. He was extremely hardworking and prolific researcher. He published about 100 papers, which are cited more than 10,000 times today, and one paper is cited over 1,000 times, and there are several papers, especially about the hydrogen molecule, that have around 500 citations today. He appreciated a lot contacts with coworkers and students. He was a very nice human being with great sense of humor. At the same time, he was very modest and unassertive. And now I would like to talk a bit about the Kołosa Medal itself. So the Kołosa Medal was established to commemorate Włodzimierz Kołosa shortly after his passing. And it's awarded since 1998. The Kołosa Medal is awarded biannually for outstanding research in theoretical, experimental chemistry, physical chemistry, to commemorate his memory. The laureate of the Kołosa Medal presents a lecture at our faculty and a scientific talk to graduate students of our faculty. The Kołosa lecture will be held today. The talk for graduate students will take place tomorrow. Laureate receives a medal with his name as a memory token, a diploma, and a honorarium. And the laureate is selected by a committee from Faculty of Chemistry, University of Warsaw. Let me briefly recount the previous recipients of the medal. As you can see, the list is extremely impressive, starting with huge names such as Roald Hoffmann, but every other researcher on the list is a huge story in itself, and every name on this list is a very, very respected and powerful scientist. And this year, I have a pleasure to say that the medal was awarded to Anna Krylov from University of Southern California for her outstanding contribution to the theoretical chemistry of open shell and electronically excited molecules in complex environments. And I will leave this slide for now, because the next speaker, Professor Tomza, will give you a more detailed description of scientific work of Professor Krylov.
Yes, so I will give you some overview of scientific life and achievements of Anna Krylov, and because the scientific achievements are plenty, it will be quite rich description. So the description was prepared together with Dr. Wojciech Skomorowski, who worked with Anna as postdoc for several years in California. So, Anna Krylov was born and grew up in Donetsk, the Ukrainian city which is currently one of the main battlefields of the war. Her youth and adolescent education coincided with the grim reality of the last decades of the Soviet Union. In those times, with the government trying to control almost every aspect of people's lives and suppressing any signs of independent thinking, acquiring higher education and conducting scientific research in natural sciences were particularly tough. It required smart navigation in the system between the need to show kind of your loyalty and the quest for individual freedom. As Anna described in one of her essays, anything from an improper poetry book to not enough enthusiastic participation in a student trip to a collective farm could get you in trouble and jeopardize your academic career. For example, she was once reprimanded for seemingly promoting an imperialistic agenda by showing in jeans at some informal school meeting. Yet, despite this hostile environment, in 1990, she completed with honors her master's degree in chemistry at the Moscow State University. Her master project was concerned with theoretical variational spectroscopy of molecules in rare gas matrices. To pursue her doctoral studies, Anna moved to the Hebrew University in Jerusalem, where she studied under the supervision of Professor Robert Benny Gerber. Her PhD work focused on the quantum dynamics of chemical reactions in molecular solids, and it was recognized with multiple awards for outstanding graduate research. She obtained her PhD degree in physical chemistry in 1996 with distinction summa cum laude. Shortly after that, she moved to the United States, where she has resided since then. Her first professional position was a research associate in the group of Professor Martin Head Gordon at the University of California in Berkeley. Postdoctoral training with Professor Head Gordon was the time when she began her brilliant research centered at the development of advanced electronic structure methods. Her target has been almost always the most notorious molecules for the quantum theories, such as radicals, open shells, or molecules in electronically excited or metastable states. After a 2-year stay in Berkeley, in 1998, Anna accepted the assistant professor position in the Department of Chemistry at the University of Southern California. The university, located right in the downtown Los Angeles, is where she has continued her academic work until now, when she became a full professor in 2008. After establishing her independent research portfolio, it didn't take long time for Anna to gain really broad recognition in the community of computational and quantum chemists. From 2000 to 2003, Anna published a series of papers that introduced the spin-flip approach to the toolbox of quantum chemistry. The spin-flip method was aimed to describe in a consistent manner the electronic structure of a molecule when a number of unpaired electrons is changing. For example, in the course of chemical bond breaking. In her pioneering works, Anna formulated the spin-flip technique within the framework of the equation of motion couplet cluster theory and also electronic configuration interaction method. Subsequently, the spin-flip treatment was also extended to other electronic structure methods such as density functional theory. The spin flip treatment is based on the observation of how the strength of the electronic correlation can be related to the relative spins of interacting electrons. By carefully exploiting the physics of electronic correlation, Anna invented a theory that allows for tackling a broad class of problems with strong correlation while retaining only a single reference wave function. And this is the key element essential for cost-efficient and broad applications of such method. Today, spin flip methods are implemented in generally available packages for quantum chemical calculations, and they are still successfully used to describe the electronic structure of radicals, of chemical bond breaking, of formation processes. For the development of the spin flip method, Anna received the Dirac Medal from the World Association of Theoretical and Computational Chemists in 2007. And this is the most prestigious recognition in the quantum chemistry community awarded to researchers under 40 years old. Later on, Anna has continued her work in the development of advanced electronic structure methodology, at the same time moving to the boundaries of its applicability to new fields and more complex molecular systems. The majority of her works are related to the method of equation of motion couplet cluster theory, and Anna contributed tremendous Anna's contribution has pushed the scope of applications of the equation of motion techniques in modern quantum chemistry. And now I will also mention few other applications of this that were essential. So she demonstrated, for example, how the equation of motion couplet cluster family of methods can be successfully applied to modeling to models of photoionization and photodetachment spectra of molecules. This was done by exploiting the flexibility of the excitation operator in equation of motion ansatz and the concept of Dyson orbital. Her developments related to theoretical photoelectron spectroscopy are compiled in the software that she developed together with her group. And this package really allows to simulate any spectroscopic observables quantifying photodetachment and photoionization processes. The methodology has proved its predictive power already, not only in the context of ionization of gas phase single molecules, but also for clusters and molecules in liquid phases. Around 10 years ago, Anna started researching another highly demanding topic in electronic structure, namely the problem of resonances and metastable states. This is one of the areas in quantum chemistry where even simple atoms and small molecules can still pose a serious challenge for theorists. Resonance electronic states, due to their unusual transient character, require rather unorthodox treatment and major reformulation of some of the standard quantum chemistry pillars. Anna, together with her research team, brought up very new ideas to the field and demonstrating how some of the already well-known solutions, like complex absorbing boundary potential, can be combined with different flavors of the equation of motion couplet cluster method to yield highly robust computational protocols. The major products of this research are modern implementations of complex valued methodologies, which are now generally available and are used to model properties of electronic resonances in molecules with highly controllable accuracy. More recently, Anna also has been interested in spectroscopy involving core excited and core ionized molecules. So this is again more complexity. This is a fast-growing area of research driven by the emergence of a new light sources capable of producing ultra-short pulses in the X-ray and XUV regimes. These sophisticated laser techniques are applied to explore ultra-fast electron dynamics in real time. Together with her collaborators in Denmark and Germany, Anna proposed innovative computational approaches to simulate various types of core-level processes, such as resonant inelastic X-ray, scattering, Auger electron emission, or near-edge absorption fine structure. All these are novel and often unique implementations of advanced theoretical methodologies which have already proven their potential to explain various experimental observations involving core electron excitations. The list of Anna achievements is long and focus on advancing electron of motion couplet cluster theory is much longer than what I just have briefly mentioned. It also includes addressing important and not yet fully resolved problems such as the description of conical intersection, charge transfer reactions, or nonlinear response properties of molecules. The equation of motion couplet cluster method is a post-Hartree-Fock method which allows the systematic and consistent inclusion of important effects due to electron correlation. As such, results from the equation of motion couplet cluster often serve as a benchmark in order to validate some more simplistic computational techniques. And this is exactly the same motivation that was pioneered in quantum chemistry by Professor Włodzimierza Kołosa, whose calculations of unprecedented accuracy for the hydrogen molecule, the smallest of all molecules, formulated the state-of-the-art benchmark and reference for theoretists and experimentalists alike. Due to its relatively high computational requirements, the applicability of the equation of motion couplet cluster theory is often limited to molecules with not more than 50 to 60 atoms. Yet, Anna, in her research, also looks into much bigger systems that are of biological significance, such as clusters or even proteins. Using a combination of advanced quantum mechanics and classical molecular dynamics, she has investigated the properties of photoactive proteins, particularly those from the family of green fluorescent proteins. Right? In her multiple papers on this topic, on this subject, Anna, with her co-workers, explained a variety of physical and chemical processes that are triggered in fluorescent biomolecules after photoabsorption. This work shows that even for large molecular systems, quantum mechanical calculation can play a pivotal role in identifying molecular structures responsible for their photophysical properties, interesting for both fundamental and applied point of view. What is particularly worth emphasizing is Anna's research. Is the effort to put into building intuition and providing some interpretations of theoretical results that are often generated by means of very complex quantum chemistry machinery. She does it through extensive developments of concepts such as natural transition orbitals or reduced density matrices. These models form a kind of shortcut between some very complicated objects like many body wave functions and physical observables. In this way, the advanced methods of quantum chemistry become less overwhelming and more accessible also to non-specialists, including maybe even organic chemists. I first met personally Anna just a few years ago. Of course, I knew her works and codes since the beginning of my PhD. In 2019, I sent my former master students to her group as a PhD student. And of course, it's obvious for everyone. I also was quickly amazed at questionable enthusiasm for doing research and genuine curiosity. The curiosity is unlimited. Her passion for science extended far beyond the areas she is the most familiar with, embracing a wide range of disciplines, from natural sciences to sociology, history, as well new emerging fields like quantum computing or quantum information. She often initiates and truly enjoys scientific discussions, not only in the lecture hall, but also on hiking trails, or what I experienced when stuck in a traffic jam in downtown Los Angeles. Anna's picture wouldn't be complete without speaking about her tremendous service to the scientific community and beyond. That includes, among others, work on editorial boards of multiple top journals dedicated to physical and theoretical chemistry research. She has been co-organizing dozens of workshops and conferences. For many years, she has been one of the chief development, now president of the QChem, a comprehensive software package for quantum chemical calculations. On the top of her nearly 300 original research publications. There are around 20 books, chapters, and extensive review papers about topics from theoretical and computational chemistry. She also delivered, of course, multiple public lectures and series of tutorials and recordings for, dedicated to young students, young researchers, and in general science enthusiasts. In terms of numbers, Anna's contribution to the education of future scientific staff is equally impressive. She supervised more than 20 PhD students. I'm not sure if including my former master or not yet on the list. And more than 30 young researchers completed their postdoctoral training in her lab. Anna also does not hesitate to take a stand publicly on important issues that affect not only the scientific community, but also our society in general. Her answer to the question why she does it is straightforward, because it's the right thing to do. And because it's the right thing to do. And because it's our duty to the next generation and an opportunity to pay our debt to the previous generations. Coming back to science. Quantum chemistry for Anna is not only about equations, numbers, and computer codes. It's also about cats. While probably all of us have heard about abstract Schrödinger cat, Anna's real kittens may be less publicly known, but they also deserve gratitude for the role in explaining the complexity of quantum molecular world. This is well documented in Anna's essay, Chemistry with Cats, where she writes about how her cats make her chemistry better. The essay demonstrates that cats may actually be very, very helpful in visualizing concepts like chirality, quantum computing, or electron spin. While the cat's example may be just kind of entertainment for a moment, it also highlights how important communication skills are nowadays, so the scientists can convey their ideas in a manner that is understandable not only to their own bubble, but to more general society. Talent, passion, and the highest standard in science science are characterizing Anna's work. She's a prime example of how a quantum chemist can build a successful research agenda that covers the electronic structure of systems ranging from simple atoms, single atoms, to biomolecules. This would be not possible without Anna's synergetic approach to theoretical research, which benefit from advances in other disciplines and at the same time is complementary to experimental discoveries. Professor Anna Krylov's achievements have already been recognized with numerous prestigious awards. I mentioned only Dirac Medal, but the list is very long, so I will stop and not mention all of them. And from today, that list has a new entry. The Medal of Włodzimierza Kołosa, awarded by the Polish Chemical Society and the Department of Chemistry, University of Warsaw, for her outstanding contributions to the theoretical chemistry of open shell and electronically excited molecules in complex environment. Dear Anna, please accept our congratulations on this new distinction and also our sincere thanks for all your fantastic contributions to our field of research. We wish you many further successes in your research and the continued joy of making amazing science.
Thank you very much for this rich introduction. As we could see, Professor Krylov is not just an excellent scientist, but extraordinary character in general, I would say. So at this moment, we will move to the presentation of the Kołosa Medal. So I will ask Vice President of Polish Chemical Society, Professor Artur Michalak. I will put this microphone for a while on site. So now I will give the floor to Professor Krylov for the lecture of Kołosa medal. I guess you will be using this one, okay.
Probably you should use.
It's all right, I can use this one. Yeah, I think that will work.
Now it works.
All right. I'm so honored and so deeply moved by this recognition. I can barely get my words together. Professor Kołosa was a true pioneer of quantum mechanics, and I remember hearing about his work and his name and the famous Kolos-Volnievich predictions when I was an undergraduate student at Moscow State in the, I believe, first class on quantum chemistry. We were told about that. I am really humbled to receive a medal in his name. And I'm also very moved by that on a personal level. And the reason for that is my connection, my family history related to Poland. So I want to begin by saying a few words about it. So this is my maternal grandmother with her father, Jan Bacmanowski, and her mother, Ganna. They lived in a small town called Bar, which until late 18th century was part of Poland, but then was moved to become part of Russian Empire. And it had Polish, Ukrainian, and Jewish population. My grandmother's family were Polish, and grandmother was fluently speaking Polish, and also Ukrainian and later Russian. She married a Ukrainian guy, Ivan Tverdokhlib, who was from a small village here, Puklyaki, near Kamenets-Podolsky region. And then they moved to Donetsk. That's where my mother was born and where we lived till I went to study at Moscow State University. So I want to say a couple of words about my grandmother because she was truly a phenomenal person. She came from a very modest background. Her father was a cobbler, and from formal education, she had just school, probably not even 10 years in Bar. But she had a phenomenal memory and phenomenal appetite to knowledge. She knew a lot of poetry and literature in Polish, in Ukrainian, and she could recite like long verses to me and my brother. And she also was an incredible person in terms of her view on the world. she lived her life as a true enlightenment person, even though she never heard of these words probably. And today when I see how many families and friendships are torn apart by partisanship, by tribalism, by politics, I often think about her because she always were able to separate people from the politics, from the institutions. For example, she was quite well versed in then informal Ukrainian history, and she had very strong feelings about the impact of Ukraine unification with Russia. She hated regime, but she never took it on Russians. She was always able to separate in her life people from the government. So, and I think that was a remarkable qualities that we need more of. So, only now I fully understand the influence, the extent of influence she had on me and my brother. And I know she would be so proud and so thrilled to see me being recognized by the Polish Chemical Society and by the University of Warsaw. And it means a lot to me too. Thank you. Thank you. So, now back to science. So one of these incredible contributions of Kołosa was the first illustration that by taking just quantum mechanics and some computing help, you can have predictive power. Predictive in a true sense of the word, when you can deliver numbers that can rival and correct experiment. So that was a watershed moment, I think, for theory. Now, since then, now we have a huge computer power, and we routinely deploy quantum mechanics, quantum chemistry, if you wish, with computers in this manner. We, not just us, just experimentalists often use these tools to guide the research, to interpret it, to make prediction, and so on. But what is interesting, it wasn't always the case that quantum mechanics was recognized not even as an important discipline, but scientifically legitimate activity. So I want to take you back to the 19th century and to the beginning of 20th century, so to say, and introduce this scientist, Ernst Mach. So he was a practicing physicist who was and a good one. He studied things like shock wave propagation and things of that matter. Here is one of the photographs that he made. He has a few laws called after him, few equations, and also if you work in hypersonic or supersonic propulsion, we use Mach as a unit of sound. Speed of sound. So 6 Mach would be 6 times of speed of sound. So, and he also was interested deeply in the philosophy of science. Now, unlike many modern philosophers of science, he was a scientist himself, so he knew what he's talking about. And questions that concerned him and his friends was, what is a legitimate science? And they came to develop this system of use called logical positivism, which, in a nutshell, very simple principle. They said that science should be based entirely on directly observable phenomena. So that sounds like a good principle, something like I would think most of us share this view now, but the caveat is that at this time, Mach and his friends in Vienna circle were considering only things that you can experience directly with your senses, your faculties, your smell, eye vision, touch, hear, that those are observable, and all the rest is not. For example, he then didn't consider all these mathematical constructs, such as quantum mechanics, to be legitimate. And he is known, for example, after Boltzmann lecture, he stood up and exclaimed, "I don't believe that atoms exist," because atoms were mathematical constructs, you couldn't see them. Now, by that, like quantum mechanics was not considered to be legitimate discipline by Vienna Circle. Now, it took a while, and after some time, these ideas developed further, and they came to the realization that what we see through the telescopes, through the lens of microscopes, through spectrometers is real and observable. But that brings me to the topic of my lecture. What about molecular orbitals? Are they real, or are they just a mathematical construct? So this is an outline of what I'm going to talk. So if you talk to a common chemist, if you tell chemist quantum mechanics, I would say that what it will evoke, a chemist will say, well, quantum mechanics, orbitals, right? So orbitals nowadays I consider to be a true native language of chemistry, in the sense that chemists start talking orbitals as native speakers before they understand the grammar. In the introductory general chemistry course, our students will use orbitals to explain why molecules are bound, why H2 plus is bound. And then, explain many more properties, reactions, spectroscopy, and so on. Now, many chemists will grow up, continue to speak the native language with great efficiency without ever learning to bother to learn actual grammar, which is quantum mechanics. But of course, here in the audience, we have experts who know the grammar. And that's what I want to discuss. What do orbitals mean in terms of real quantum mechanics, and also in terms of connection to the experiment? Are they real? Are they real in a logical positivism case? So I will answer this in affirmative, but first let me start with some simple, I do not know why I have this, maybe if I move here, maybe it will be a little bit better. All right, let's see. Okay, I think it's better. So, orbitals. No, it's not. If we consider something very simple, one electron system, such as H2+, then everything is simple. Orbitals, they are just wave functions. They are solutions of Schrödinger equation. And as such, they would be directly mapped into the observable. If you want to calculate a property, you will take some matrix elements using these orbitals. So, however, as we move to many electron systems, for example, 2 or 3 or more electrons, then things become much murkier. We can arrive to the concept of orbitals in approximate treatments, such as, for example, Hartree-Fock mean field model, where wave functions are approximated by this anti-symmetrized product of molecular orbitals, and we can think about them as states of pseudo-independent electrons. Well, this is good, but even here we run into problems. For example, as we well know, if you have a Slater determinant like that, any linear combination of these orbitals will give you exactly the same energy and exactly the same properties. So, do they make sense then, individual orbitals? Now, if you go beyond this very simple treatment of electrons and move into correlated wave functions, then the situation becomes much murkier, because our wave function would be linear combination of many determinants, and then the meaning of individual orbitals become lost. So, 2 questions. Do orbitals make sense for interacting electrons for many body wave functions? are they real? And by real, I mean, are they related to directly to experimental observables or not? Now, I'm going to answer this question in the affirmative, and my guiding light here would be experiment. So orbitals are real, but in order to, but not any type of orbitals. So let us first consider some simple situation. Let us talk about photoelectron and photodetachment experiments. Let us consider initial state in this case, which is a, maybe it's interfering with this. All right. Okay, so that's better. So let us consider photodetachment or photoionization experiment. Let's start with closed shell system, and then we kick out one electron and put it in the continuum. So can we use molecular orbital concepts to describe this? Well, let me show you a few equations, and they are related to the experimental, what we see experimentally. So the key object that is related to experimental measurement here is this matrix element, which we call photoelectron matrix element, which is initial state, dipole moment operator, and final state, which is this ionized core and free electron. So from that, you can calculate cross sections and so on. Now, you can further integrate this equation and collapse it to such a simple form where we have here matrix element between something that we call Dyson orbital, free electron state, and dipole moment. So what is Dyson orbital? Dyson orbital is kind of an overlap between n and n-1 electron states. And it's an orbital because it depends only on coordinates of one electron. And it directly enters into the observable. So in this way, it's related to the experimental observable. And importantly, this expression is valid for n-electron wave functions. You do not need any approximations here. So these two states, two wave functions, can be exact full CI, they can be strongly correlated, and what's not. Now, if you put something approximate to remind some well-known concepts, if we, for example, put here Hartree-Fock wave function, a single determinant, and another determinant from which we remove one orbital, we end up with canonical Hartree-Fock orbitals. And they are indeed Dyson orbitals obtained from an approximate wave functions. But this concept can be extended to any wave functions, and then these orbitals can directly be used to compute experimental observables, such as total cross-sections, using these matrix elements. And then you can compare experiment with the theory and see if you get correct cross-sections. Now, you can get more sophisticated observations. For example, as you can see from this diagram, if you have here S-type Dyson orbital and you come up with the polarized light along this direction, you end up with a P-wave for outgoing electron. And that could be directly measured experimentally. Here is this beautiful image from my friend Andrei Sanov, and it shows where electrons are flying for ionization from H-. If you have p state, like for example iodine minus, then from this expression you immediately can derive selection rules, which will tell you that you will have S and D wave, and surely enough you see signature of this in the photoelectron images. So this is how you can directly map these orbitals to the experimental observables, and these orbitals therefore are physical reality, because you can connect them to experiment. So, Dyson orbitals give rise to experimentally observable quantities, and they can be defined into any wave functions. There are no approximations. You do not need Hartree-Fock theory for that. Now, you can probe angular distributions of photoelectrons, and that give you information about shapes of Dyson orbitals and so on. All right, so this is one type of real orbitals, but is that all? What if you are not interested in photoionization? can we use orbital concepts to describe electronically excited states, such as, for example, UEVs, spectra, or X-ray absorption spectroscopies? Here we have initial and final state having the same number of electrons, but we excite electrons. Well, here we can follow a similar approach, and the instrument that is allowing us to introduce orbitals is a reduced quantity called one-particle transition density matrix. So here is a definition of this object in terms of second quantization, and physically what it means is that this quantity allows us to map initial state into final state with single electron excitation, one electron excitation at a time. So it just tells us how to get this from that, not the whole wave function, but one that is described by single excitations. Now, what is important, even though we do not have like the full wave function here, this quantity contains all required information that we need to obtain experimental observable, which is in this case is matrix element of dipole moment that gives us oscillator strength and polarization of the transition through this simple expression. So it contains all necessary information. Now, it's a much simpler object than two many electron wave functions, and we can think about it as people call this object exciton wave function, for example, and you can think about it, it's a change of electron density upon excitation. It tells us from where you remove and to where you put electrons. Okay, so it's a nice object, two-dimensional, and we can plot it. Here are beautiful pictures from Shaul Muka-Melvok, where they used this concept of exciton wave function or transition density matrices to analyze results of the calculation from this dimer, two porphyrin molecules. So they computed excited states, and then for different excited states, they plot these maps. So these are just how atoms are numbered. So these are just atoms in two rings. And then, by looking at these maps, you can identify local excitations that are localized on one ring at a time, or you can identify charge transfer states where you have these off-diagonal blocks. So from this, you can see really what happens with electron density upon excitation, and you can connect it to experimental observables, such as intensities of these transitions. Okay, so this is very useful, but where are the orbitals? Well, the moment we have matrix, we can work with it. And we can, for example, diagonalize this matrix. In this case, it's non-symmetric matrix, so we do not diagonalize it, we do singular value decomposition. But the essence of it is that we can collapse the matrix into the most compact possible form. And then, when we do that, we can obtain objects, the same exciton wave function or transition density, can be expressed as in this form, where we have now only one index, only one k, and we have these pairs of orbitals that are coming from this transformation. One has a meaning of whole orbital from where we remove, and another has a meaning of particle orbital, that's to where we promote electrons. And they come in pairs, and there are usually just a few of them. These coefficients are telling their relative contributions. So, why is it useful? Why this concept is useful? Here is a very simple example, calculation of excited state in a uracil molecule. So if you run your calculation, and I took very simple one, and then you look at the amplitudes of wave function, and you attempt to assign character of the state, what it is. You can see that in this wave function, the way it comes out from the calculations, you have quite a few amplitudes with similar weights, and these are like orbitals from which I excite and to where I excite. So if you just look at this picture, you can say, well, this is a very complicated state with complex character and so on. And it will be wrong, because if you take this transition density and compute this natural transition orbitals, you end up with this. So all this complexity is artifact of the flexibility and of making these transformations, and SVD gives us just one pair of orbitals that describe this transition, well, 99% of it. So, and you can see that it's a very simple wave function and it's essential character of this transition. So, the beauty of it is that you can do it for any wave function or density functional to that matter, and you can see what is the essential character of transition. And here is an example from coupled cluster calculations for steel band, and I show two states. One is dominated by just one pair of natural orbitals, another one has two, so you can see how they are different. And what is very important is that because of the connection to the matrix elements and the observables, from this you can immediately see why this transition is very bright. If you steep dipole moment operator between these two, you have bright transitions. And here, even if you do not see symmetry label, you can see that you cannot have a bright transition here. So, very useful concept that allows us to get physical insight and talk about orbitals in these many-body calculations. All right, so excited states, we have orbital picture, but what if we are not interested in this linear traditional spectroscopies? What if we want to understand non-linear transitions, such as, for example, two-photon adsorption spectroscopy? In this case, we also can talk about initial state and final state. They look like that, but we do not really excite, promote electrons by one photon. We have two photons, and they get simultaneously adsorbed. People draw a picture like that, often saying there is a virtual state in there, but there are no virtual states. You do calculations, and this is one excited state, this is the second one. So, can we use orbital picture here? Here is a two-photon spectra of SLN, and I can, in principle, because I have my states, calculate just regular natural transition orbitals. And I show them for these three lowest transitions. And so they look like that. You excite from pi, from HOMO in the SLN to these three orbitals, which look like diffuse p-type orbitals. So that's all right. But looking at these orbitals doesn't tell me anything about actual experimental observable in this case. Because these orbitals are not, I cannot recreate from them my cross-section. And I cannot, for example, explain why this state is much brighter than this state. They all look the same. So, and the reason I cannot do it, because for two-photon cross-section, there is this complicated expression where we have not some matrix element between initial and final state, but some overall states, all of them. So, looks terribly complicated, but it turns out that we still can design and describe this complex expression in terms of molecular orbitals, and to do that, we need to do a little bit more work, and it turns out that if you look at this expression, we can realize that we do not really care about all these intermediate states. Because if I sum up over all of them, this part of the expression gives me first-order perturbed electronic states. And I can compute them. And if I compute them, I actually can rewrite my observable in this form, when I have my initial state and perturbed final state and dipole matrix moment between them. And I will have a second term where I will have perturbed initial state and a final state. So this is actually exactly how we compute these properties in quantum chemistry. We never do sum over states. We solve these response equations, and it immediately suggests that I can introduce a new object, a perturbed density matrix, which is a map between my initial and perturbed final state plus my perturbed initial state and the final state. And then I can look at these maps and I can do SVD and I can obtain natural orbitals for these perturbed states. And these orbitals will be directly related to experimental observables, in this case cross-sections for two-photon transitions. And here how it looks for ethylene. So this is one-photon natural transition orbitals are not related to the two-photon cross-section. And here is how two-photon orbitals look like. If I go with XX component, this is two pairs that I get. So, and these orbitals, as I say, represent perturbed final state or perturbed initial state. So basically here you see what this virtual state, mysterious virtual state actually is. It's a perturbed state of this type. If you come with another polarization along the axis, this is your virtual state, and that what will help to explain the magnitude of the cross-section. So, you can take it further for other nonlinear processes. We did it for resonant inelastic X-ray scattering. My former postdoc Mark and Stefan Grimmer, they did it for other response properties. So it works, and it allows us to understand nonlinear observables using simple molecular orbital picture. So, to conclude this part, transition density matrices, reduced quantities, they are representing compact and experimentally relevant information about electronic transitions. And from them we can compute natural transition orbitals of different types, and they give us essential picture of excited states, and they also directly related to the observables. So by looking at them we can understand the observables. So you can extend this concept further. As I showed for nonlinear properties, you can do it for spin-forbidden processes and so on. All right, so is this all? Well, spectroscopy is a very rich field, and there are many different types of spectroscopies and phenomena. And recently we became interested in two electron processes, such as, for example, Auger processes. When you create a hole in the core orbital, and then such states decay by filling the hole and ejecting one electron into the continuum. So it's a two-electron transition. So in a cartoonish way, I can describe initial state like this, and this is my final state, and the question is, can I put an orbital picture on it? Can I introduce orbitals? Now, again, I want to follow experimental observable here, and the relevant experimental observable is the lifetime of these states or rate of the decay for different channels, and we can compute it using this golden rule type of expression that's worked by Wojtek Skamarowski. And again, these are many electron wave functions, free electron state, and again, as in the case of Dyson orbitals, we can collapse it into such expression where I have just this simple quantity which looks like, almost like transition density matrix or Dyson orbital, but it has three indices instead of one. We call them two-body Dyson orbital, and if you look at this picture, you see that you really need to move 3 electrons to get this description of this process. Now, we can compute this thing, and then we can perform singular value decomposition of it to extract, in this case, triples of molecular orbitals. So here is an example for benzene. We can have a core natural orbital and 2 decay natural orbitals. So, and from that we can get essential picture of 2-electron process such as Auger decay. So, here is how it looks for benzene. There are different channels, and you can see that some channels are described by just one set of natural Auger orbitals. In some you have 2. Sometimes, you know, they have these interesting shapes and so on. So it works very nicely. Again, it gives you molecular orbital picture, which is not grounded in an approximate treatment, but derived from the many-body wave functions and can be related to observables, in this case, decay rate. Now, in case of benzene, what you see here, it kind of you could have guessed this picture by looking at canonical Hartree-Fock orbitals and wave functions corresponding to decay channels. But here is an example that would be very confusing if we didn't have these tools. Here is a calculation of 3 decay channels, there are a lot of them, for this system, OH radical, or OH minus anion, and 4 water molecules, simple model system. So we create a hole in OH, core electron, and then we calculate different decay channels for Auger process. So the 3 lowest ones are shown here, and if I want to understand from where these Auger electrons are coming, if I look at the amplitudes of my decay channels, I see like a mess. I see many similar amplitudes, and it looks like something very complicated. So, but if I use natural Auger orbitals and compute them, the picture actually becomes very simple. So we see that for this channel, these are natural Auger orbitals. We have exactly 2 sets of them, nothing more. Here also 2 sets, and here 2 sets. So all this complexity is collapsed. Now, what is also cool, if you look at these orbitals, you will see that for this channel that has largest decay rate, we see larger contribution from OH minus. So this is local Auger decay. But for this channel, for example, we see more contributions from waters, which suggests that this is ICD type of decay channel. So from these pictures, we can make conclusions and explain the magnitude of experimental observables. All right, so we can use orbital picture to 2 electron processes like Auger decay and similar, and again, using the same set of techniques and tools. So now I want to leave the domain of normal bound quantum chemistry and go into the continuum. So let me ask if we can use orbital concepts for states that are embedded in the continuum, electronic resonances, such as states that lie above detachment or ionization threshold. So, well, that could sound like a very complicated task, because in the continuum we do not even have discrete states. But it turns out that we can tackle the continuum problems using non-Hermitian quantum mechanics, which is a very rich set of methods. I will talk about it tomorrow in more details. But the essence is that we can map continuum problem into such picture where we can think about this state in the continuum as a result of bound state, which is localized, L-square integrable, and very easy to understand, coupled with the continuum. So, and if we do that, we get imaginary energies, which you would never get in Hermitian quantum mechanics. And these imaginary energies have the meaning that you have real part represents the position of the resonance, and imaginary part represents the lifetime. Now, importantly, so we get L-square integrable wave functions out of it, and because of that, because we have wave functions, we can deploy the same machinery and compute natural orbitals or Dyson orbitals for these complex valued wave functions, and we will get now transition densities that have real and imaginary part. Now that will never happen for you in Hermitian quantum mechanics, because densities are real, but here they become imaginary. And then we can look at real exciton wave function and imaginary exciton wave function. And you will get pictures like that. This is Cn minus radical, one state. Real part looks like sigma to pi star excitation. And imaginary part looks like that. Here we have another state. Pi to pi star looks like something you would expect, but then this is imaginary part of the same transition. So what do they describe and what these orbitals are related to? Well, they are related to these complex energies. They are related to experimentally observable properties such as lifetime, and this imaginary part of these excitons is related to how the states decay into the continuum. You can look at much more complicated things like this type of anions, where you can analyze different partial decay widths and rationalize what you get by the shape of these real and imaginary excitons. All right, so we can take orbital picture to the continuum and introduce molecular orbital picture to describe the states, just as we do in normal quantum mechanics. All right, so this is just a summary of orbital concepts in many body theories. So in incomplete summary, we have many more examples, but the bottom line is that we can work with very large and complicated, giant, if you wish, many body wave functions, but we can introduce molecular orbitals related to different type of processes, transitions, and experimental observable. Dyson orbitals, natural transition orbitals, natural response orbitals, natural Auger orbitals, and we can do it for real and imaginary densities as well. Okay, so you might be thinking, all right, so orbitals can be mapped to the observables. So you can judge the quality of the orbitals by the quality of observables you compute from these orbitals. So that's, I think, is simple, but can we actually see them? So in a sense that Mach thought, but maybe with the help of a few more devices. And the answer is yes. So there are a series of experiments that aim to do exactly that. So here are images obtained by STM for molecules put on surface. So this is a porphyrin molecule placed on surface, and you modify voltage, and you can pump electrons into this molecule or suck electrons from this molecule and look at the STM images. And look at this. So depending on the voltage, you have these different shapes, and you can compare them with Dyson orbitals computed for this molecule, and you can see just incredible mapping and resemblance between computed orbitals and images. So there are many more examples like that. So this is really working, but you may say, and you will be correct, that these are not orbitals. These are densities, because these are squares of the orbitals, right? Because you do not really see the faces. You see nodal structure, but not faces. So can we get something which is more close to orbitals? And here is an example from another experimental group using very different technique. In this case, photoelectron spectroscopy again. And what they do photoelectron spectroscopy with angular and momentum resolution, and they do it for molecules on the surface. Now, what it does, it allows you to align molecules, so which helps. So you do not need to average over molecular orientations. And what you see here is that it's a signal that you get here, which is in this case, it's written in momentum gauge, but the deal is the same. You have initial state and you have free electron state. And that's actually, you can think about it as your Dyson orbital in momentum space. You can obtain it from this here. Now, there is no phase here, but they have a technique for the phase. Now, the moment you do this, and to get your Dyson orbital in momentum space, you can do Fourier transform and get it into the real space. And what is shown here is the orbital reconstructed by this experiment for this long molecule. And you can see how well it resembles the computed orbital. And again, there are like a few additional steps here, including Fourier transform and some fixing of the phase, but I think we are getting pretty close to seeing molecular orbitals. Now, would it convince Ernst Mach that we can see them? Or maybe if we have to do 3 Fourier transform, it doesn't count anymore? I do not know, but I think it's an interesting set of experiments and the way to push quantum mechanics to the limit and see how far we can take it. So, to conclude, orbitals are real, but not any type of orbitals. So, orbitals that are related and derived from experimentally observable quantities. Now, what kind of orbitals you have? Well, for different type of experiments, you will have different orbitals. So what you see will depend on what experiment you follow. Now, it may be disturbing, but I think it's actually quite consistent with quantum mechanics, where the observation is not independent on the system. I think orbital concepts are very useful in the context of spectroscopy, but in order to make full use of this, we need to follow the observables and derive orbitals that are relevant to specific experiments. Or we can design perhaps new observables and do new experiments. Now, orbital reconstruction is possible, but with caveats, and some of these experiments are still considered to be controversial, but I think it is possible, maybe not perfect. So to conclude, I would like to thank people who did all the work, my current group, including Pavel, who is about to graduate, and a stellar team of former students and postdocs whose results I showed today, Koshik Nanda, who is now in QCAM, Pavel Pohilko, now with Dominikas Git in the University of Michigan, Wojtek Skamarowski, who is here at Warsaw, Samir Gozem at Georgia State University, Thomas Yagau, KU Leuven, Ksenia Bravo at BU, and Mark de Vergifosse at also Leuven, but other half of it. And finally, I want to get back and to Kolos, and I want to say a few words about inspiration he provides to scientists today. We heard a lot about his remarkable scientific achievements and his pioneering work, which is true. But he also was a man of courage and integrity. So here is a quote from this short but very nice article about him, which says, "In the years of communist power in Poland, Wlodek never compromised his political and moral standards. Neither Wlodek nor anyone in his group was ever a member of the Communist Party, an unusual situation in those years." Now, it wasn't just unusual. It really required moral courage, and it could have serious career consequences. Now, many people living in this time in different countries under socialism rule were less brave and choose to compromise and collaborate with the regime. Now, we do not want to judge them because we do not know how it was. Well, we know, but we do not want to judge them, but I want to emphasize that we should take inspiration from people who didn't compromise, from people like Kolos, and draw inspiration for today. And inspiration we need, because today we see, unfortunately, the return of the same old illiberal ideas, Marxism-Leninism, that comes back, slightly repackaged and renamed as critical social justice or diversity, equity, and inclusion. And we see how these ideas are being propagated and subverting science. And in order to oppose them, we need courage. And I hope that we will get courage by being inspired by Kolos' life, remarkable life and achievement. Thank you.
Thank you very much for this inspiring lecture. The floor is open for questions.
there is often an overlap. For example, if you look at lowest ionized states, it often will be something which is very similar to canonical HOMO. And then when you look at lowest excitation in molecules, it often will be HOMO to LUMO excitations. So you will see resemblance in shapes often, but quantitatively they are different things. And you can see the consequences of it when you calculate observables. For example, if you take just canonical Hartree-Fock orbitals and you calculate something as simple as total cross-section, you will see very visible deviations from the experimental result. And when you use correlated Dyson orbitals, you see better agreement. So there are parallels, but quantitatively they are different things.
It's not a question, but more of a comment. That I was a bit surprised that you started from spectroscopies, although I understand, of course, the incentive. But let's say, for someone who does not believe, like Mahmoud, orbitals exist, probably the best experimental evidence would be something that you actually talked about at the very end, namely tunneling microscopy. So this porphyrin case that you picked up, I don't think it's the most fortunate one because it's a complex molecule with extremely many possible excitations, a contribution from different atomic entities into the orbitals and so on. But people have obtained beautiful images for polyaromatic hydrocarbons, so like pentacene or hexacene and so on, and a blind person would believe, seeing these images, that this electron density images, that orbitals are beyond them, It's just that we need to find a phase. But they are so convincing because it's a good example because first of all, you deal only with carbon and hydrogen in these molecules, and these orbitals that you are accessible in experiment in some bias, positive or negative, are exclusively carbon orbitals, exclusively pi orbitals. And yet there are many because it's a large molecule. So, as I say, a blind person would immediately believe it. So, let's say this would also add nicely to your schematic pictures because it's a new schematic, namely for example, all orbitals are occupied all the time, but you transfer one electron to the virtual orbital. So it's still a new scenario. And modeling this would, I think, be immediately straightforward.
You are right that there are many more pictures, and I think it's a matter of taste which one speaks more to you. Now, the reason I picked this example, actually, I have my reason. And here, what you see here are Dyson orbitals computed using density functional theory. Now, what is interesting, the authors kind of talk a lot about it, but basically they tried first to look at HOMO and LUMO canonical orbitals that coming from Constant DFT. And they get like no resemblance. So basically in this example, they were able to get this, I thought, pretty decent agreement because you can see, how they are different, only when they did proper Dyson orbital calculation using approximate wave functions. That's all right, but they couldn't get it with orbitals. And what they see again, if you look at the voltage, okay, you can see HOMO and LUMO, and what is nice that you can see contributions of different atoms, this metal or these aromatic rings. But I do agree that when you see these many different examples of very different classes of molecules, then when you really start to believe, right, that, that must be real.
Yeah, of course. But I still think that the fact that you need to define those orbitals differently for every type of experiment is its major weakness. So that
my weakness, its
right?
strengths.
You
I think
so?
It's great.
Well, from didactic viewpoint, I would disagree.
Yeah. All right. Okay. I think.
It's more a comment, since we entered now this educational thing. So what I am always saying to the student when I talk about orbitals, what is an orbital? Tell me. And most of them would not give you the correct answer. This is a one electron wave function. This is an orbital. And you cannot see a wave function. I mean, you said it, but we should avoid the impression that we see a wave function. We may see a density or an expectation value of the one electron wave function, and this then gives you an idea about the shape of the things. So we don't see orbitals.
I guess there was one more question over there, right?
Again, as a point to Wojtek, it's kind of true that the orbitals have to be defined differently from different process, but if you adopt, like in the talk, second quantization, then actually it appears to be very similar. Like there is very natural way of defining these orbitals if you adopt second quantization. So in some sense, they are not universal, they're not the same in each process, but they are defined in a very similar way in each process, if I understand correctly.
Yeah, that's exactly right. And again, you know, like I understand the desire to have a single set of orbitals, but I think it's a wrong desire. So we should embrace that. There are true orbitals for different occasions.
Yes, but they will be different in
the mechanism by which we define, like you said, is the
exactly. Same. So they will be different, but the mechanism how you obtain them and construction of the formalism is exactly the same. You sandwich creation annihilation operators between final state and initial state, right? And so the prescription is the same.
Correct. Yeah, I agree. Thank you.
I guess there was one more there. It's gonna be tough to get there, I guess. So could you please pass the microphone?
It's a question in relation to what you were talking about. Actually, there is a technique which we can use to visualize bands in solid-state physics. I mean, angular resolved photoelectron spectroscopy. And as I understood you correctly, you have shown only non-angular resolved, non-angular resolution, right? In this technique.
No, this is angular result. You won't be able
okay, so
to
this
get,
is the same technique as in
that's
solid
the same
state.
technique, and you're absolutely right. You can get band structure from it when you do it for solids. Yeah, there are experiments, and they use for interpretation the same sort of thing.
Okay, thank you.
Thank you.
Are there any further questions?
Maybe following also Michał's question. So if I would like to reconstruct many body wave function from this kind of observable, so the Dyson is on the one electron level. So what would be the next step from the spectroscopy to somehow add higher level correlation to somehow design the scheme that ultimately, I mean, can you reproduce fully the many body wave function by the set of like this kind of one electron Dyson orbitals, then two electron or some kind of general?
I mean, that's an excellent question, and I do not really have answer to it, but we definitely can climb up this hierarchy and go to two-body, to geminals, which we can obtain by looking at two-particle density metrics or two-particle transition density metrics. We can go to three bodies and so on, but then you need to think how you look, what is the experimental observable that will deliver this information. And then, you know, maybe you can bring, like, I do not know, 10 lasers and set up experiments that will give you sufficient information to map one into another. But I think reconstructing the whole thing would be I mean, it will be exponentially.
Yeah, because this is probably the question to spectroscopists. I don't know, just not pointing
I think
spectroscopists.
there
I
are
mean,
more qualified people
because in cold atoms, we can somehow, because they are very resolved, we can really go to the two-body densities, free-body reconstruct from experiments. But I was wondering if chemical spectroscopy can do anything like this.
Yeah, well, there are excellent experimentalists in the audience, so maybe they can answer this.
Okay, anyone else? Okay.
So when chemists are using quantum chemistry, so real chemists are using quantum chemistry, they usually want to have some localized orbitals, like natural bond orbitals, from which they can explain bonds, and this means that this orbital should not extend over the whole molecule, but they should be just localized, so just lone pairs, maybe two bonds, maybe two atoms, 3 atoms are extreme. And what do you propose for them? So should they abandon this concept of NBO or similar concept which are quite widely used in?
I mean, a great question. Now, my knee-jerk reaction is to tell that we need to re-educate them and tell them that these localized orbitals do not exist, because if you take this molecule and photoionize it, you will create this delocalized orbital extended over the whole thing. But maybe we can find a place to localized orbitals if we can think about some smart experimental observable, which I do not know what it is, because, if I think about, say, bond strengths, right, I do not really have, the bonds in the molecules are not really independent. If you have like ethylene molecule and you look at CH orbitals, they're all delocalized. And if you kick electron from this orbital, you will have effect in all CH vibrations. I do not know how you can localize it. So, yeah, I think, as temptation is great to think about localized orbitals, but I cannot think about sound justification for that.
Thank you.
Okay, anyone wants to ask the question? Well, if not, let's thank our laureate again.
Thank you.
And just a reminder that tomorrow we will have a seminar at 11 a.m. Location Old Library at the Faculty of Chemistry building. Feel invited.